Hello and welcome back, my dear students. So today I'm going to cover with you section 8.5, which will be the last section to learn a new test that you can use to check for convergence or divergence of a series. From 8.2 up to 8.5, you were learning tests to check for convergence and divergence. Here you learn the last two tests, which are the ratio test, and there's another one, we call it the root test. And you will learn just another type of convergence where we call it the absolutely convergence or conditionally convergence. All of that will take place in section 8.5. Now, by the end of this section, you'll be done with all of the tests. What I'm expecting from you here, just please try to study all of these 4 sections and then start to try to solve problems in general. You look at the series, you need to check for convergence or divergence, see what's the best test that you can use, okay, for that question. Now, if we think back about all the tests that we covered before, okay, I need you just to think again about the integral test, the comparison test, limit comparison test. With all of these tests, there was always one condition. If you go back to them, you'll always see a condition that AK, the terms of the sequence, should be positive terms. With the alternating series, even with the alternating series, yes, it was of this form and it has some negative terms, but yet they have the condition that AK should be positive. And it has the alternating part only from -1 to the power of k. But still AK should be positive, but it has like plus minus negative positive terms controlled by the -1 to the power of k. So it goes with a certain specific pattern. Okay, now sometimes we face a series that it has negative positive terms, but they are not alternating series. How can we deal with this series? How can we check their convergence? The idea here is really simple. What we need to do, just take the absolute value. Remember the function of the absolute value always. Just we change everything. They change the terms into positive terms. So for example, if I think about the sine k over k to the power 3, this sequence here, the sine k over k to the power 3, I know here that the terms should be sometimes positive, sometimes negative. Remember that the sine range is what? Between -1 to 1. So these terms, if I add them as a series, they'll be sometimes positive, sometimes negative, but they don't alternate signs. So they don't have the same pattern like alternating series. So for these type of questions, even with the alternating series, by taking the absolute value, we'll solve the issue of negative terms. And then if I take the absolute value and I check again if it's convergent or divergent by using any suitable test that you can use. By this, if with the absolute value I get a convergent series, then I can say that the original one is absolutely convergent. So again, if with the absolute value it's converges, then the original one is absolutely converges. We'll call it absolutely converges. Okay? Now, which one is stronger when we say absolutely convergent or normal convergent? What you need to know that the absolutely convergent is stronger. So anytime if I have any series as absolutely convergent, this implies that this series is convergent. So it's a stronger condition. So if I have it absolutely, it implies to convergent. But what about the opposite, the way back? If it's convergent, doesn't mean it's absolutely convergent? No, not necessary. So if it's convergent, but not absolutely convergent, so if it's convergent, the way back, but not absolutely convergent, in this case, we call it conditionally convergent. So if it's convergent, yes, but not absolutely convergent, we'll call it conditionally convergent. So now there's 2 types for us. One of them with the absolute value, I call it absolutely convergent. But if with the absolute value, it's not convergent, but originally it was convergent, I call it conditionally convergent. I call it conditionally convergent. Okay. Now, for that purpose, what can I do when I face any question with this? Maybe negative terms, maybe alternating. What we can do is just following a flow chart that I'll show you in the next slide. But first, let's try the idea as simple equation. We'll try this example and then we'll do the criteria, what to do in these questions. So let's say I have something like this. This is example 5.1. We need to determine whether this series is absolutely convergent or not. So what can I do? I always start with what's AK. AK in this question, this is alternating series, by the way. You could use the alternating series test if you like. But it's easier to deal with the one with the absolute value. So AK is with the negative sign, okay? Negative 1 over k plus 1 over 2 to the power of k. If I take the absolute value for AK, the absolute value will get rid of the negative 1. So it's now 1 only over 2 to the power of k. Okay, now think about the series with the absolute value of AK. How about this series? We need to check if it's convergent or divergent. This is the one with the absolute value. I could combine them both with the power of k, from k equals to 1 to infinity. Now, once you take the absolute value, you think about it as a new question. Look at this question. What does this series looks like? This is a geometric series. We know clearly this is a geometric series. And I can easily say that this is convergent geometric series. This is convergent geometric series. Why it's convergent? Because the absolute value for I, which is equals to half, less than 1. Okay, so now I know that this is convergent geometric series. That's fine. So with the absolute value, it's convergent. So what should be my conclusion in this case? So I can say that hence the original series is absolutely convergent. Okay, if the original series is absolutely convergent, can I say that it's convergent? Yes, for sure. The absolutely always gives normal convergence. But I need the absolutely. Why not? It's stronger. So I took the absolute value. I've checked. It's absolutely convergent. That's it. Now, what we'll be doing now, I'll try just to show you this flow chart, just to help us to work with these types of questions. What can I do? Especially with the conditionally, what should you do with these questions? So firstly, the best advice I can give you with any of these questions that it could have some negative terms, you could use it also for the alternating series test. You always start with taking the absolute value, okay? I take the absolute value. Now look at the question as a new question for you after you took the absolute value. What's the best test that you can use? Maybe it's ratio test that we'll cover today, maybe it's root test, maybe comparison, maybe integral test, any of the previous tests that we covered already or coming this section. So with the absolute value, decide which test you use. And then now, after you use that test, if it's convergent with that test, I can say that this is absolutely convergent. If not, then we always try with the original one without the absolute value. So the priority always with the absolute value. If it's not convergent, then I use the original one without the absolute value. And most of the time we use the alternating series test. But not always, but most of the time, especially if it's alternating series. I'm gonna use the alternating series test. Or else it depends on the series that we're seeing. Now with the other test, if it's convergent, so this is conditionally convergent, you see? It's convergent, but not absolutely. That's why we call it conditionally convergent. If not, I say it's divergent. This is the best way to solve these questions to determine whether the series is absolutely convergent, conditionally convergent, or divergent. Okay, this is the easiest way. Now let's try to solve one extra question. This is a famous example that we already practiced before in 8.4. We need to determine whether this alternating harmonic series, remember this is a famous series that we know already, the alternating harmonic series, if this is absolutely convergent or not, or whatever. We need to check everything. So I need to know if it's absolutely or conditional or divergent. So what can I do for this case? I know this one with the absolute value of AK, okay? This equals to what? 1 over K. And so sigma, the absolute value of AK equals to what? Sigma 1 over K. What about this series? We know this one. This is the harmonic series. So with the absolute value, this is divergent harmonic series. We already did this before. This is with the absolute value. With the absolute value, it's divergent. Okay. Without the absolute value, so sigma AK alone, without the absolute value, which is the alternating harmonic series. Remember, we saw this in 8.4. You can easily use the alternating series test, okay? And by using the alternating series test, it will be converges. So if it's converges, but not absolutely converges, so I can say directly, hence the original, okay, now we'll talk about the original one, hence the original question. The original series is conditionally convergent, Okay, and this is a very good example of what? Conditionally convergent, the alternating harmonic series. Okay, good. Now we'll check one more. We'll go back to our first question with the sign. Now this one with the sign, we know that this sometimes positive, sometimes negative. So if I start with the absolute value for AK, this equals to what? The absolute value for sine of K over K to the power of 3. Now, remember again, once you take the absolute value, you need to think what's the best test to use. Remember, from the previous sections, I told you any question with sine, cosine, tan inverse, these trig functions, sine inverse, cosine inverse, these, the best test that you can use is the comparison test, the direct comparison test. Why? Because we know they are less than what? So for the sine, we know that it's always less than or equals to what? 1. The sine always less than 1. Over, it's still K to the power 3. No need for the absolute value because this is always positive. K minimum 1, so this is always positive. So this is less than 1 over K to the power 3, which I can call as BK. What do we know about this BK? We know that sigma 1 over K to the power 3 from K equals to 1 to infinity is a convergent P series. This is a convergent P series. Remember, the P series is convergent if P is greater than 1, just like this case. Now I'm comparing with something convergent and it's less than. So this is the case, remember from our previous studying. So this is the case of the large one convergent. So if the large one convergent, then the smaller one convergent. So I can say that hence sigma, the absolute value with the absolute value from k equals to 1 to infinity is convergence. Is convergent, sorry. Now, if with the absolute value is convergent, so what about the original one? Right? If with the absolute value convergent, what can I conclude about the original one? So sigma, the original question, sine of k over k to the power of 3 from k equals to 1 to infinity is absolutely convergent. Is absolutely convergent. Okay, since it's with the absolute value convergent. Fine. So that's why every time it's much better to start with the absolute value. Even with the alternating series test, by the way. So usually once you learn this method, no need again to use the alternating series test unless you need to check for conditionally convergent. And this is really useful. You can still use it, but it's not necessary. So anytime I see alternating series test, take the absolute value. If you're lucky and it's convergent, you're done. It's absolutely convergent. If not, then you have to use the alternating series test. Okay, especially with the question that asks you to use to check for absolutely convergent or conditionally convergent. Okay. Fine. Let's see what do we have next. Remember, if it's absolutely convergent, so that's mean it's converges as well. Remember, the absolutely is stronger. Okay, one more. Now I'll give you a good hint that you can use for all the upcoming questions. Every time you have a rational function, like this is a rational function, right? Polynomial divided by another polynomial. Anytime the difference between the numerator and the denominator is only 1, so this one will be conditionally convergent. So this is like a self-check step. So again, anytime when you have rational function and the difference between the degree of the numerator and the denominator is only 1, which basically you can compare with 1 over n, so this is conditionally convergent. It will be conditionally convergent, okay? Now, let's try with this one. Let's do this last one fast. So if I take with the absolute value sigma, the absolute value of AK from K, or here this time they use N. Anyway, you can use N from 0 to infinity. This is equals sigma. With the absolute value, you get rid of the negative term. So this is a 3n plus 4 over 2n squared plus 3n plus 5 from n equals to 0 to infinity. Okay. Now, what type of series is this? This is the one which looks like rational function. Remember from before, we said with rational function, the best test that you can use is the limit comparison test. The best one I can use is the limit comparison test. So you see, after I take the absolute value, I think again, what's the most suitable test that I can use? Okay, limit comparison test. What do I need to compare with? What should be BK in this case? If I use the limit comparison test, BK should be 1 over n. What about 1 over n? What do we know about sigma 1 over n? From n equals to 0 to infinity, we know that this is divergence harmonic series. This is divergence harmonic series. Harmonic series, okay. So this is divergence. Now we need to try with the limit comparison test. Remember the limit comparison test, it says what? We need to divide limit of AK, but this time the absolute value, over BK from K. I keep using K because we're used to use K more. This time we've used N. As N approaches to infinity, and this is equals the limit. You can do it yourself directly. So this is times N over 1. So this is a 3N squared plus 4n, down it's 2n squared plus 3n plus 5 as n approaches to infinity. If you find this limit just by only multiplying by 1 over n to the power of 2, 1 over n to the power of 2, you can do it in your head as L'Hopital. So this limit, you can easily show that this is equals to 3 over 2. And remember, for the limit comparison test, we need to check if this is greater than 0. And yes, it's greater than 0. If it's greater than 0, then both of them, they have the same behavior. So that means it's divergent. So hence, by limit comparison test, sigma with the absolute value is divergent. So does it mean we're done with the question? No. So once I check with the absolute value and it gives divergent, then what do? I'll go back to the flow chart just for you to check. So this is what I've done. I took the absolute value. Okay, I took the absolute value. I checked using any suitable test. I got no, it's divergent. So we're not done yet. I'll go back with the original one without the absolute value, then I'll check using any other test. Most of the time, the alternating series test. Okay, this is what I have to do, this square. Okay, let's do that. So now we checked with the absolute value, it's divergent. Now I have to check without the absolute value. Let's continue in the next slide. So now I'll check without the absolute value. So check sigma AK. From K equals this time from K, this is N. Sigma AN, N from equals to 0 to infinity. Okay, let's check. I'll use the limit comparison test. So use the alternating series test. Alternating series test. So what should be our first condition to check? I need to check that the limit of an as n approaches to infinity equals to 0. Okay, limit n approaches to infinity. What's the question in this case? We have it as okay, let's check. So 3n plus 4 divided by 2n squared plus 3, 2n squared plus 3n plus 5. This limit equals to what? 0. Okay, first condition satisfied. Now I need to check the second one, which is the decreasing one. So I need to check an plus 1 over an. This is equals to what? 3 an plus 1. This is an plus 1. So this is a 3n plus 1 plus 4. Down it's 2n plus 1 squared plus 3n plus 1 plus 5 times reciprocal of an. 2n squared plus 3n plus 5 over 3n plus 4. I need to expand and simplify. Okay, we need to expand and simplify this. If I expand and simplify, what do I get? Okay, try to expand. So you'll get in the numerator, this is a 3n plus 7 times 2n squared plus 3n plus 5. Down you will get, you need to expand this. So this is n squared plus 2n plus 1 times 2. So this is 2n squared plus 4n plus 2 plus 3n plus 3 plus 5. And here I have 3n plus 4. If you compare these two, you'll notice that you'll have the numerator smaller than the denominator. So this is less than 1, which is decreasing. So this is the second condition, it's decreasing. Once I check that this is equals to 0, this is decreasing, so I can say that hence the original The original series is what this time? So using the alternating series test, it's converges. And with the absolute value, it was divergent. So this is what we can say that this is conditionally convergent, okay? This time is conditionally convergent. So again, as I told you, anytime you notice that the difference between the numerator and the denominator degree is only 1, so just like you compare with 1 over n. So most of the time you'll get, in this case, conditionally convergent. Okay, so this is the process to check this type of questions. Hopefully the idea of absolutely convergent, conditionally convergent is clear now. But remember again, every time you start with the absolute value, you have to start with the absolute value. Okay. Now we'll move to the test that we can use. This is a really useful test. We use it with a wide range of series. Many questions we can use the ratio test. Basically, most of the time, any question you see like exponent, like a number, if you have any number, a constant, let's say a to the power of k, exponential function, anytime you have factorial, anything with factorial, k factorial, anything with factorial, I could always use the ratio test. These are two famous cases for the ratio test, exponential and factorial. Okay, what does the ratio test says? The ratio test says that if you take, we have sigma of ak, okay? If I divide ak plus 1 over ak, just like the one we use for increasing decreasing, with their absolute value, and you take the limit as k approaches to infinity. So we divide ak plus 1 over ak with the absolute value, and you take the limit. If the limit exists and it's equals to L, then if L is less than 1, this value is anything less than 1, so this series is absolutely convergent. So the ratio test always gives the strong result. It's absolutely convergent. If L is greater than 1, including infinity, so we say it's diverges. If L equals 1 exactly, so it gives no conclusion. That's when you need to try another test. Okay, this is very useful test. You need to check the conditions. Remember, the only useful one for us if it's less than 1. It's convergent, absolutely convergent. More than 1, diverges. Equals to 1, try another test. There's no conclusion. Okay, and it's easy to apply. We already used this before and we practiced this. When do we use the ratio test? Anytime you have something like exponential, if you have factorial, if you have the question mixed between exponential and polynomials, we could use the ratio test. So let's see one question. How can we use the ratio test and what do we get? Something like this. So as you see here, we have it as alternating series and it looks like exponential and it has k. Do I need to think about alternating series test? No, it should be always the last test you try. No need. Just try with the absolutely convergent, better with the absolute value. So what do I do? What can I do here? I'll take what's the absolute value for ak. It's equals to what? K over 2 to the power of k. Then I need the absolute value for k plus 1. Just as we usually do with increasing decreasing. So this is k plus 1 over 2 to the power of k plus 1. Okay, now divide them by each other and take the limit. As k approaches to infinity, we divide ak plus 1 divided by ak, and this is equals the limit. K approaches to infinity, so I need to do k plus 1 over 2 to the power of k plus 1 times the reciprocal for ak, 2 to the power of k over k. Okay, that's good. See if there's any cancellation. Clearly, I could cancel 2 to the power of k with 2 to the power of k plus 1. What will be left? Only 2 to the power of 1. Can you cancel k with k? No. Be careful. These are together. So we can't cancel k, and since the operation here is addition. So now what do we have then? What's left? I have the limit. After simplifying, in the numerator I have k plus 1. Down I have 2k. As k approaches to infinity. Now check this limit. What does this limit equals to? So if you multiply by 1 over k and down by 1 over k, this will be equals to, clearly you know it's half, but we need to show this extra step. So limit 1 plus 1 over k, and down I have 2, only 2. As k approaches to infinity. Now this limit equals to what? This is 0, and this is equals to half. Now remember with the ratio test, what's the result? We have half. Think here. Half, it falls into which one of these 3? It's less than 1, so this is the absolutely convergent. So this is equals to half, and this is less than 1. So I can say that hence the series is absolutely convergent by the ratio test. Remember, you need always to mention which test did you use. By using the ratio test. Okay, it's absolutely convergent. So remember always, the ratio test always gives absolutely convergent, not only convergent. Okay. It's easy test. It's really useful. We can use it many times. So it helps us a lot to decide if it's convergent or divergent. Okay, now let's try something else. Try one more. Another question for the ratio test. This one. Again, remember ratio test, anytime you see factorial, use ratio test. Exponential, use ratio test. A combination of both, use ratio test. So we'll check how can we use ratio test, and no need to worry about the alternating series. Just get rid of this negative part by the absolute value. So now the absolute value for AK, it's equals to what? K factorial over e to the power of k. What's the absolute value for AK plus 1? This is k plus 1 factorial over e to the power of k plus 1. Now we'll do the process as the previous question. You take the limit and then you divide these by each other, and this is equal. It's always good to prepare them in advance, the AK and AK plus 1. Now once you divide, remember we do what? We start with AK plus 1 and then we multiply by the reciprocal of AK. So this is EK over k factorial. Okay, now I need to see if there's any simplification. So this is limit. We multiply and simplify. K plus 1 factorial is basically k plus 1 times k factorial and e to the power of k. Down, e to the power of k plus 1, I could split it, k e to the power of k times e to the power of 1. K factorial. As k approaches to infinity. See what can we cancel out. K factorial with k factorial. E to the power of k with e to the power of k. Great. What should be left in this case? So we end up with limit. In the numerator I have k plus 1. And down I have only k. It's as a constant. So k approaches to infinity. So by this, the limit will be equals to 1 over e. Clearly, this is 1 over e times, let's do it down. So this is equals to 1 over e times limit of k plus 1 as k approaches to infinity. And this one, we know this is goes to infinity. This is equals infinity. Okay, so this limit equals to infinity at this time. Let's go back to the test. So if the limit is equal to infinity, then the series diverges. Anything more than 1, it's diverges. Okay, so hence the series diverges by the ratio test. Ratio test. Okay, so we saw 2 examples. One of them we had it less than 1, so we said it's absolutely convergent. Here it's more than 1, which is basically infinity in this case. So I could say that this is diverges, and you remember you have always to mention which test you have used. You need to say, I've used the ratio test. Okay, now what if we saw the first example about the ratio test, it was less than 1, so it's convergent. Here we saw something greater than 1 or infinity, and it's divergent. What if we have equals to 1? Does it give me any conclusion? If we think about these 2 famous series, like this one, 1 over k, we know this harmonic series, right? And we all agree that by now, we know that this is divergent. If I try to apply the ratio test for this one, for 1 over k, if I try to use the ratio test, I'll end up with the limit equals to 1 only. And if it's equals to 1, so there's no conclusion, even though we know it's divergent. But since it's equals to 1, so the ratio test is not helpful. I can say nothing about it. So there's no conclusion in this case. Now another case, even though originally we start with divergent, but it's end up with a ratio test equals to 1. Maybe we can use the ratio test for this P series. We know that this P series is convergent already. So if I try again to use the ratio test in this case, it will give me again 1. So there's no conclusion. So you see, if you get 1, it means nothing. Maybe it's divergent, maybe it's convergent. So you can't decide. Okay, hopefully that's clear about the ratio test. Again, ratio test is very useful. We'll use it a lot. In all these coming sections from 8.6 till 8.8, we're going to use all ratio tests with power series, Taylor series, all of these series, we're going to use basically ratio test. So it's very important to understand and remember the 3 cases. What do you conclude according to the value of L? Now, one last test, which is usually still we can use the ratio test, but this is easier. We call it the root test. Basically, they use the root test once we have anything with a high power. So if you have anything to a power, so I use the root test. Sometimes we have it they're like something to a power of k. Maybe sometimes you find them like fraction, but both of them to a power. This is k power k. So anytime we have high power, we can easily deal with it as a root test. And what does the root test says? If you take the kth root, remember I take kth to cancel the power. So power k, how do I cancel it? With kth root. So if I take the kth root with the absolute value, remember all of these tests with the absolute value. The kth root of the absolute value of ak, if it's equals to L, exists and equals to L, so we have the same 3 cases that we had them with the ratio test. Less than 1, absolutely convergent. More than 1, including infinity, diverges. If it's equals to 1, there is no conclusion. You need to try another test. So let's see our last example for today, something like this one. We need to use the root test to determine if it's convergent or divergent. Do I need to use the absolute value here? No need, as they are already, we can take the absolute value just in case, just to follow that in general for your future. So I'll take the absolute value for AK. It's 2k plus 4 over 5k minus 1. They are already positive. Now I need to take sigma for the kth root of the absolute value of AK. This is with the power k. K equals to 1 to infinity. Kth root will do what? Will cancel out the power. So this is sigma 2k plus 4 over 5k minus 1. From k equals to 1 to infinity. From k equals to 1 to infinity. Okay, that's the sigma. Now what do I need to do with this? No need now for the sigma, I need the limit, sorry. So we need to take the limit as k approaches to infinity, limit as k approaches to infinity. Now this limit clearly will be equals to what? 2 over 5. And this is less than 1. So we can easily say that hence the series is absolutely convergent. Okay, and by this we're done with the last test for this chapter. Okay, if you check here, you can find all of the tests that we covered with their when to use them and the conclusion that you can get and where did you learn it, in which section. So we covered the integral test. We know the P series as a famous series, the comparison test, limit comparison test, alternating series test. Now, if I need just to help you when to use each one of them, remember the integral test when the question is easy to integrate. If it's easy to integrate. Basically, most of the time, if there's ln in the question, exponential, 1 over x squared plus 1, something easy to integrate. I can use the integral test. The comparison test, after you learn the limit comparison test, I advise you to use the comparison test only if you have trig. Like if you have sine, cosine, tan inverse. With a trig, it's easier to use the direct comparison test. Limit comparison test, it's like wider. We can use it for more questions. Basically, you can use it for the questions with rationals, okay, like fractions, or anything involves radical, like radical, let's say 2x plus 1. Anything has radical, and also here with rationals. The alternating series test, you can use it in general, but for me, I prefer that you use it once the question you need to check for conditionally convergent. Like from now on, no need just every time to use the alternating series test. Only if you need to check for conditionally, use the alternating series test. Or else, no need to worry about the negative sign. Just take absolute value and that's it. Now, with the absolutely convergent, we know what to do. Ratio test, it's really good. We can use it with anything with exponential, factorial. We can use the ratio test. The root test, anything, as I said, just involves exponential, like but high power. Power k for all. You take the power for all, we can use the root test. What I'll be doing with you next time, now since you learn all of the tests, I'll add one video for problem solving. Generally questions, and you need to decide which test to use, which test is the most suitable for that case. And I added for you into Mika and also into the Blackboard a flow chart for all of the tests and what's the best test that you can use according to the question. So if you see the question, you decide which test to use. That's it for today. Next time, after the problem solving, we'll start with the power series.